So let's take what we just did and extend it to a 4 pi electron system, 4 pi orbital system. See if we can come up with the pi orbitals for butadiene. This is C4H8. Now, how many total orbitals are there? Total 16 plus 8, 24 total orbitals. You'll notice that all 6 of the hydrogen 1s orbitals are in the plane, as are the 3 2p x and 3 2p y and the 3 2s orbitals. So 24 of those orbitals we can ignore, right? They won't be at the frontier, we don't have to worry about. Sorry.
We can ignore all
So
24.
20 of those orbitals we can ignore, right? Because 20 are in the plane. Right, 3 from each carbon and then all of the hydrogens. So there are only 4 pi symmetry orbitals. We know that the frontier will be in those. So we can figure out what those pi symmetry orbitals look like. We can predict the reactivity. So we know there are going to be 4 orbitals. We know they're going to gradually increase in energy.
And it's we don't use 20, we only use the 4 because there are 2 pi bonds in the structure.
Well, this is a plane of molecules. So if we define the plane of the molecule as the xy plane, then 2px, 2py, 2s, and 1s all lie in the plane. What that means is that the 4 2pz orbitals are the only ones that are available for bonding in the pi system. We do have 4 pi electrons. But the key isn't that we have 4 pi electrons. The key is that we have 4 pi orbitals. Because the electrons don't all have to be filled, right? As we saw with the cation, right? We have 3 pi orbitals, but only 2 pi electrons in the electron cation. We know they're gradually going to increase, and the number of nodes is also going to increase. So there will never be any nodes in the low energy orbital. But as you go up, the number of nodes will increase, and for a linear system like this, the number of nodes is always going to be n minus 1, where n is the number out of the pi orbital. Right? So 0 nodes for pi 1, 1 node for pi 2, 2 nodes for pi 3, 3 nodes for pi 4.
What would be a not linear system?
A rate like a benzene ring.
Oh, okay.
With a benzene, there's only one way to chop a linear system in half. Right? There's only one way to chop a line in half. If you have a molecule that lies in a plane like a benzene ring,
Gotcha.
there's 2 ways of cutting the plane.
Okay.
And if you have a molecule that lies in 3 dimensions, there's 3 ways of cutting a cube. So there are 3 possible 1-node orbitals for a 3-dimensional molecule. But there's only one possible 1-node orbital for the linear, the string system. Generally, molecules that have the same number of nodes have the same or very similar energies. The number of nodes, every time you tell electrons where they can't be, and a node is a place where there's 0 chance of finding the electron, every time you tell the electrons where they can't be, they get pissed and their energy rises. Electrons want to occupy all space simultaneously. So what we're going to do is we're going to draw the system of 4 orbitals, and then we're going to try to figure out where those nodes are. and what that orbital will look like as a result. And the electrons are sitting in a box somewhere. There are 4 pi electrons in here. And once we've created these orbitals, we will fill them. The simplest thing to do is to keep everybody in phase. Right? No nodes, everybody's in phase. We've got an orbital that allows those electrons to extend over all 4 nuclei. That's the stability orbital. Those electrons are driving the extra stability because we now have 3 bonding interactions, bonding with respect to every basic pair. One node is going to go right down the center of the molecule. So we'll have constructive interference on the left-hand side between carbon 1 and 2, and we'll have constructive interference between carbon 3 and 4, but we'll have a node down the center of the molecule. Which means that they can either be bonding the 2 pairs of N carbon, but they're anti-bonding with respect to carbon 2 and carbon 3. So there's 2 bonding interactions. C1, C2, C3, C4, but there's 1 anti-bonding interaction. With respect to C2, C3. So how many net bonding interactions are there? There's 2 bonding interactions, but there's 1 anti-bonding interaction. So when you talk to the electrons, there's only 1 advantage, right? If there's the same number of bonding interactions and anti-bonding interactions, then you're going to be non-bonding because there's no benefit. Carbon 2 and carbon 3, when you talk to them, they're not that happy because they're not in phase. But it's still a bonding orbital because it still has net bonding. Still lower in energy than the original P. So the original P orbital energy level can kind of be put in the center here. We're going to drop pi 1 and pi 2. We're going to raise pi 3 and pi 4. Pi 3 got raised by about the same amount as pi 2 dropped. And pi 4 got raised by amount that pi 1 dropped. These are going to be relatively equal spacing. I don't know if I actually managed to draw them to scale, but the distance between these should be about the same. If I do that well. So what does pi 3 look like? Where are those nodes? In general, don't put them through nuclei unless you have to. In this case, we don't have to, because we can put them there. So we're going to have pi orbitals and p orbitals on the 2nd and 3rd carbon in phase with one another, and out of phase with each other. So we should have constructive interference between these guys. So we have 1 net bonding, or 1 bonding interaction. It's basically the opposite of pi 2, right? It's bonding with respect to carbon 2 and carbon 3, but it's anti-bonding with respect to the others. So there's 1 net anti-bonding interaction. Does it make sense that having one net antibonding interaction would raise your energy by about the same amount as one net bonding interaction would lower it? Yeah. So how many net antibonding interactions do we expect up here?
2.
We need to raise it by the same
Just
amount.
kidding.
Right? We need to raise it by the same amount that that dropped. So if 3 bonding interactions drops it by this much, we'll need 3 antibonding interactions to raise it by that same amount. The way to do that is just put nodes between all the nuclei. Right, so the highest energy orbital always looks kind of like the uninteracting orbitals. It's just nodes everywhere. This has 3 antibonding interactions and no bonding interactions to compensate. So these 2 are antibonding. We can put stars on them to indicate that those are antibonding. Ideally, if you want your system to be stable, what you'd like to do is fill your bonding orbitals and leave your antibonding orbitals empty. So now we have the 4 electrons, we can put them in. Where are we going to put them? Our principle says put the first one there. As long as this gap is bigger than the spin pairing energy, then we'll pair that up. Then we'll move the next one up there. And again, as long as this gap is larger than the spin pairing energy, then we'll put that one there. So pi 1 and pi 2 are filled, and pi 3 and pi 4 are empty. And that means that the system is happy, right? It's to its advantage to form these bonds because the orbitals are lower energy. The electrons are lower energy. Where's my frontier? Where's my HOMO?
Pi 1?
So pi 1 is the stability orbital. That's not the lowest, right? That's the lowest energy orbital, but it's not the highest energy filled orbital. The HOMO is pi 2.
Oh, okay.
And that's the highest energy occupied orbital. That's where that abbreviation comes from.
That makes sense. So the other one would be what we know?
And the
Pi
HOMO
one.
is the lowest energy unoccupied orbital, which is pi 3.
Oh, just kidding. Wow.
Right? If you want electrons from this system, it's going to give you its highest energy orbitals, which means it's going to give you electrons, which means it's going to give you the ones that are in pi 2. If you have electrons and you want to give them to this system, you're going to have to put them there. That's the lowest energy orbital available to you. So the frontier is here, pi 2 and pi 3. Do pi bonds generally act as nucleophiles in reactions or as electrophiles?
Electrophiles? Well, I think it depends.
What do we generally add to pi bonds? What reactions of pi bonds do we talk about?
Like the pi bond attacks something, so that you say it's a nucleophile.
Yep. So this is electron rich. Generally it attacks electrophile, like bromine, for example. So the pi bond acts as a nucleophile. So which orbital do I care about most in terms of reactivity of the pi system?
HOMO?
That one. So this is the stability orbital, and this one's the reactivity orbital. If you want to know how the molecule reacts, look at pi 2. Pi 2 conveniently looks very much like that Lewis structure. Right? It's got a pi bond between carbon 1 and carbon 2. It's got a pi bond between carbon 2 and carbon 3. The bond between, or 3 and 4. The bond between carbon 2 and carbon 3. That's still an ordinary single bond. This looks like this resonance structure. And you would probably not draw this resonance structure. It is a legitimate resonance structure, right? You haven't done anything except move electrons, so it's very much consistent. But it's got unpaired electrons. But that's what the LUMO looks like. The LUMO looks like a orbital or a Lewis structure that's got a load electron on each end and a pi bond between the center. So if we did the same reaction on this 1,3-butadiene that I just showed for the cyclohexene over there, what would that look like?
Can you say that again? Sorry.
Yeah, we're going to add bromine to 1,3-butadiene in a second here. So let's take 1,3-butadiene and the active is bromine. Try to figure out the mechanism back there. So which orbital attacks the bromine? Right here. So we're going to attack bromine. And make a new carbon-bromine bond. Normally when we attack bromine, we make a bromonium ion. Where the bromine is bonded to both of those simultaneously. And then that bromonium ion waits until bromide ion comes and opens it up. In this case, we don't have to form the bromonium ion to stabilize it because this is a little carbocation. We've got a nice 3-pi orbital system here that looks very similar to the 3-pi orbital system we just drew for the unsubstituted orbital carbocation. And there's a resonance structure you can draw for this that's got positive charge out here on the end. Which one of these two resonance structures is the major contributor? One on the left or the one on the right?
The one on the left.
This one, why?
It's more stable because it's more substituted.
So this is the secondary carbocation. This one is the primary carbocation. That's primary. So if you're a bromide ion, which carbon do you want to attack?
The positively charged.
Well, there's two positive charged carbons. Which of those two is going to take you less energy to interact with?
I think the one with the full positive charge.
The one with the larger amount of positive charge, right? So there's more positive charge on this carbon than there is on that carbon. If I were to draw this system out and indicate the positive charge from the partials, I have a bigger partial positive there, and a smaller partial positive here, and I've got my pi electrons, right, interacting across all three nuclei. So if you're bromide, this is the better electrophile. So the kinetically controlled product will look like this. This is a 1-2 addition. Notice that the initial bromine always has to be attacked by an N. Because if you put the bromine on the middle, you have a primary carbocation that's not an orbital. Right? So you can't stabilize it. So the ends of the system are always the reactant, not the center of the system. And that's actually because if you look at the orbitals in detail, the orbitals aren't completely symmetrical. The bonding orbital more electron density at the ends and less in the center. And the anti-bonding orbital actually has more electron density in the center and less on the ends. So if you look at the shape of kind of the structure of this orbital, my 3 star is mostly localized on the center, whereas pi 2, the bonding orbital, doesn't have as much electron density in the center particles. So that's the kinetic product. That's the most stable carbocation, which is going to be the one that takes less energy for the nucleophile to attack. The other product, if bromine attacked this, would look like that. That's a 1,4 addition product. Which one's more stable? The product of 1,2 addition or the product of 1,4 addition?
Product 1,4.
1,4, this is more substitutable bond. That's the thermodynamic product. More stable disubstitution type bond. So if you add bromine across this, you're going to get a mixture of 1,2 and 1,4 addition. If you do it at low temperature, the 1,2 addition product will dominate, but if you raise the temperature, then the more substituted double bond, the thermodynamic product will dominate. Because you're introducing equilibrium conditions. If you raise the temperature so that bromine can fall back off, you can regenerate the allylic carbocation, and eventually bromine is going to attack here, and that's less likely to reverse because that's the more substituted product. So you have an energy diagram for these two reactions. Where over here you've got the more stable product. Over here you've got the less stable product. And it takes less activation energy to get there than it does to get there. Anytime you have a situation where the lower activation energy leads to the less stable product and the higher activation energy for the more stable product, you have the possibility of having either kinetic control or thermodynamic control depending on the temperature of the reaction.
Wait, why is the one that's kinetically controlled farthest right? Wouldn't that be the first one to form?
I'm showing it on one diagram with the reaction coordinates can go in either direction from the carbocation. It can go either this way or that way. It was arbitrary which one I decided to draw on the left and which one I decided to draw on the right.
Okay, thanks.
The 1,2 addition product isn't necessarily an intermediate on the way to the 1,4. You can form the 1,4 without going through the 1,2 first. It's just that if you allow the reaction to reverse, right? If you've got enough energy to go over this activation energy barrier for the reverse, then you've also got enough energy to go over that activation energy barrier and you'll get to your more stable. Whereas you might not have enough energy to go over this even larger. So kinetically, the more positive charge is on this carbon, and it wants to get attacked more readily. But thermodynamically, you'd rather form the internal double bond. So there's always that kind of competition between the 1,4 addition to generate the more stable product and the 1,2 addition. It's possible to extend the pi system even further. We had 135 hexatriene, and we treated this with ATR. point we predict would be the product. HBr, concentrated HBr.
Would it take all of the double bonds away or just one?
It depends on how much HBr you put in there. Let's assume we're going to put in one and one. So that it only adds one for a while.
Isn't this electrophilic addition?
Yes. Electrophilic addition is the reaction you know on pi systems. Unless it's a cyclic system, in which case electrophilic aromatic substitution. The acid source is hydronium ion, right, because concentrated HBr or HBr is associated. So you're going to react. Where are you going to react?
One of the ends, I think?
One of the ends. Why? Because if you react on one of the ends, the carbocation that you form is now part of a 5 pi orbital system. It's kind of an extended allylic system. You can actually draw resonance structures that move that positive charge now. I'm drawing the hydrogens out only on the end because that's the one we just added one to. So that you can keep track of which carbon we added to. Right, so there's resonance stabilization. But we've got a 5 pi orbital system here. What's that look like? Since it's an odd number of pi orbitals, there's going to be a non-bonding orbital in the center. You have 2 bonding orbitals and 2 anti-bonding orbitals. And we're going to put our 4 electrons in there. The HOMO is pi 2. The LUMO is the non-bonding orbital pi 3. But that's the reactivity orbital because the carbocation is reacting. The orbital that makes it particularly stable is pi 1. That's the one that allows the electrons to extend over all 5. So if you were to want to draw these,
Why are there only 4 electrons?
because it's a cation, so there's this pi 1,
Okay,
this pi 1.
that's
and
why.
there's
We're
no
not
electron
starting
on it.
at the original.
The original is a 6 pi orbital system.
Right, okay.
The 6 pi electron. And you can extend it, and I think I did in one of the pre-recorded videos. So this is 0 node orbital. Where those electrons can extend over everybody, right, all 5 nuclei. So it's bonding with respect to C1, C2, C2, C3, C3, C4, and C4, C5. So how many net bonding interactions? Every adjacent
5.
pair. So 1, 2, 3, and 4. This
Hold on,
one's going
you
to have
have
a
5
single
dots
node.
though.
What's that?
You have 5 dots though.
Yeah, those are the nuclei.
Oh, gotcha.
So this is C1, C2 bonding, C2, C3 bonding, C2, C4 bonding, C4, C5 bonding. C6 is over here, that's the one with the hydrogen on it, so I didn't actually draw it. Because it's not part of the extended pi system.
Okay.
So I'm going to put one node in right down the center of the molecule where it needs to go. No contribution from that orbital. 2 net bonding interactions. bonded with respect to C1, C2, bonded with respect to C4, C5, and no interaction between C2 and C4 because they're too far apart. Pi 3, 2 nodes, they're going to go through carbon 2 and carbon 4. Zero net bonding or anti-bonding. And no contribution to that system from carbon 2 or carbon 4. That's the reactive orbital. There's 3 possible places I could put the electrophile that correspond to where the positive charge is on the 3 different Lewis curves. I don't really need pi 4 and pi 5 star because the reactive orbital is this one. But if I wanted to, I could draw them. Pi 4 is a 3-node orbital, so it looks like this. Net anti-bonding. No interaction between carbon 2 and carbon 4 because there's a node through carbon 3. Right, 2 net anti-bonding goes up by the same amount as 2 net bonding goes down. And if I wanted pi 5 is always the top one is always the one that's got nodes everywhere. So you've got anti-bonding with respect to every adjacent pair or that anti-bonding. So what's the product going to look like? There's 3 possible products, right, that I could draw from this. Almost like that. This. Like that. So I can get 1-2 addition, I can get 1-4 addition, and I can get 1-6 addition. Which is the most stable product?
1-4 or 1? Is it 1-6? I don't know if the more in between is better.
We've still got a conjugated diene, so that's stable. And both of those double bonds disubstitute. So this is the thermodynamic product. Which is the kinetic product.
1,
2. This product sucks. This one at least still has a conjugated diene. This one doesn't. This is an isolated pi bonds. Which means 1-4 addition is the least stable product. The carbocation is roughly equally stable here as it is there, because those are both secondary carbocations. But obviously this one forms first because that's where the carbocation and the Su's added. So you're going to get a mixture of 1-2 and 1-6. Maybe you'll get a little 1-4, but not very much, because it's not very stable. And if you heat it up, you'll get the 1-6 addition, add to the 2 ends and generate the internal diene. And if you don't heat it up, and you run it at a low temperature so you can't get equilibrium, then you're going to get that kinetic product where you get the terminal diene. So it's similar to Markovnikov and anti-Markovnikov addition. Right? Markovnikov addition would generate a more stable product. So there are pre-recorded videos The other thing you'll notice